Yeah, connect.
Good afternoon and welcome. The session starts in 9 minutes. We're just waiting for everybody else to join. I'd just like to confirm with you, Chair, if you can hear me.
Yeah.
Two of our presentations will be pre-recorded videos.
Cool. Okay, yeah, I can hear you.
Great, thank you. The two pre-recorded videos are the speaker from Egypt, Mohammed Darwish, and the gentleman from the Northwest University in South Africa.
So what I missed that.
Sorry, I was just making sure you are aware of the two pre-recorded presentations.
Oh, okay, I didn't know. Okay, so I will just put that there.
Yeah, so it's the presentation at 2:15 and 2:30.
Okay.
And as I'm sure you're aware, I will play those recordings out once you have announced them.
Cool. Yeah. Hi, can you help Emma with his link? I think he's getting some problems.
Who is it that needs assistance?
Emma, so the guy from, wait 1 second. Burkina Faso, the second talk.
Second speak. All right, cool. I will ask
Yeah.
someone to resend it to him.
Yeah, cool,
Okay.
thanks. Hello everyone, so welcome to the next session, 11th session, so before the last. So this session is mostly dedicated to stellar astronomy. We will have 5 talks in this session. So we will start with Johnson Urama, who is from the University of Nigeria, and he will be presenting his work on neutron stars. So up to you, Johnson.
Good afternoon, everybody. It's my pleasure to be part of this conference. And I'm just trying to share my screen from here. Yeah. Okay. And well, my presentation is on neutron star glitches, the unending riddle. And I hope the screen sharing is working. I hope you can see the screen. Oh, okay.
Yeah. Good.
So, well, by way of introduction, I'm Johnson Urama from the University of Nigeria, Nsukka. And the topic is on neutron star glitches, the unending riddle. And well, just a little background because we know some may not be so used to neutron stars, some may not be pulsar scientists. And the neutron star is one of the endpoints of stellar evolution. They are typically one of the most densest objects you can think of apart from black hole. It's just the next thing to a black hole. And the neutron stars are mostly, they manifest mostly as radio pulsars. And so radio pulsars are the most common observable manifestation of these fascinating objects. There are many different manifestations of the neutron stars. And like we've listed there, the rotation powered pulsar, which is the commonest manifestation, the magnetar, soft gamma ray repeater, XP, and so on and so forth. All those are different manifestations of neutron star. And just creating the background still, that there shows us the internal structure of what is believed to be a neutron star, which has a radius of about 10 to 12 kilometers. and it is made up of the outer crust, made up of the outer crust is solid. It has an inner crust and outer core of superfluid neutrons and possibly superconducting protons and electrons. But one thing about these neutron stars is that they are about the most stable objects in the universe. Their pulses come so precisely, and they can be timed with a very incredible, they are very incredibly precise. And so the timing also, they provide us almost the best clock in the universe. But even with this incredible precision, they still have a number of timing irregularities. And the commonest ones are glitches and timing noise. We are focusing here on the glitches. I was just trying to create the background for those who may not be into neutron star or pulsar studies. So the glitches here are constitute one form of the timing irregularities. And these are just deviations from the predicted spin down. And what is a glitch? Okay, typically we see a glitch here, like these jumps here indicate there are jumps. This is a particular pulsar we observed using the radio telescope trial in South Africa. It has a large jump here, and there's what looks like a small jump here, if you can see my pointer. And these are supposed to be either very small glitches or timing noise. That's part of timing noise are just like glitches, but these are smaller jumps. And so that is basically what a glitch is, this discontinuity, this jump in the regular spin down of a pulsar, and they come in different sizes. Like if we are fractional jumps in their rotation frequency of the order of 10 to power minus 4 to 10 to power minus 7 are usually classified to be large jumps, while those smaller than such are said to be small jumps. Of course, there are even jumps that are small as 10 to power minus 7. That is fractional change in the rotation rate, and that shows us the level of precision involved in the timing here. And looking at this plot, we see typically about 600 pulsars. And among these 600 pulsars, some of them have had large jumps, some have had very small jumps. There is also what we can see as medium jumps here. And when we begin to discuss, that's part of the challenges, because if you look at this diagram, we have large jumps only mostly among pulsars in the age bracket of 10,000, 1,000 to 10,000 years. That is about 10 to power 3.5 to something like 10 to power 4, 10 to power 5. Just these, they are called the useful pulsars. Before then, the very young ones, they have mostly very small jumps. And also the elderly ones also have mostly small jumps. And this occurrence of glitches, especially different size of glitches, and different behavior signatures is one of the things that pose challenges to this understanding this neutron star stability, because the glitches occur in with various signatures. Some of them even we've had what is even referred to as an anti-glitch, and these are some of the riddles we are going to talk about that we have observed in glitches. So, but basically, one of the principal things, one of the main contributions these glitch observations is making to this field is that it serves as a window into the interior of these neutron stars. because glitch observation is one of the things that make us to understand how these neutron stars really look like. I mean, the interior. And it's from glitch observations that we actually begin to understand that part of it could be superfluid, because if it's just a solid all through, some of the behavior will not manifest. And so glitches have been observed for over 50 years now. Pulsars were actually first observed in 1967, and just shortly after that, glitches were also recorded. Just less than 2 years after the first discovery of pulsars, glitches were observed, and ever since then we have continued to observe glitches. And for all those 5 decades, pulsar scientists, neutron star scientists, and other theorists have been trying to come up with different explanations about different behavior. And until now, it's still not, there are a lot of things still we are still struggling to understand some of them. And we still hope that with time and maybe with more glitches, some of these things can become clearer. One of the challenges here is trying to have a dividing line between those glitches, the micro and macro glitches on one hand, and the micro glitches and timing noise on another. Because some of these glitches, looking at the sizes, some of them, there is actually difficult to draw a dividing line where the large jumps start from and where it ends and where the small ones start. And also for the small ones to be able to differentiate them from what is just called timing noise. I know in the literature some glitches, some small jumps have been, some jumps have been reported as glitches, and in some other literature they have been classified as timing noise. And so one of the challenges and a number of works are still going on that, trying to have a dividing line, and because that will help us to even understand better the origin, the mechanisms of these jumps, whether there are glitches or timing noise, they are all jumps. The only thing is that timing noise are more of a random fluctuations, that are smaller jumps. And the pulsars that provide us most of these observations, at least near real-time glitch detection, are usually mostly the Crab pulsar and the Vela pulsar, because for these 2 pulsars, there are observatories that are monitoring them for the period they are up, and they have been monitored so intensely. And from those observations, glitches have been almost caught as they happen, and subsequently the recoveries have also been continuously monitored. And from those 2 there, we see that they exhibit quite different characteristics. And one of the characteristics is the overshoot observed in Crab, where when the recovery, sometimes the crust tries to decelerate below its normal steady state angular velocity after the jump. Such does not happen in Vela. And you also see that Crab pulsars are normally in the past been small glitches, while Vela have been large glitches. That's just some of the things. There are actually so many differences between Crab and Vela, and there have been different interpretations, but still, a lot thing is to be understood. Of course, some have attributed it to the age difference between them, but whether that is able to really explain everything still needs to be proved. Here we see that from the recovery component, the helium parameter measured in both pulsars. For Crab, we have a helium parameter represented by Q there, which is about 0.2, while for pulsar is about 0.12. What do this mean? This just tells us, because with this recovery parameter, we can begin to estimate what the interior will look like. They are like the thickness of the crust, and also the mechanism that can lead to the glitches. And with those Q values, we can see that for crab pulsar, with those Q values consistent with the starquake model, where the glitches are caused by starquake, just like an earthquake, by this one happening in the neutron star. But
you have 1 minute.
Sorry?
You have 1 minute.
Okay, 1 minute. Okay. So we will not explain that of Vela. So the mechanisms are likely supposed to be different. And if there are different mechanisms, if for glitches, and in the same neutron star, does it mean that there are different, are they really different? These are some of the riddles we are still trying to unravel. Like this plot here, we see, well, these lines were drawn by eye, but we are looking at some of the rotational parameters as a function of glitch activity. And looking at this, it appears that we have two groups, the crab type and the Vela type. Is this real or is it just imaginary? We are still trying to understand that. And partly we can see, and it goes across pulsars of different ages and different rotational frequencies. And these are some of the reasons, because well, as we try to probe into this, it will help us to understand the mechanisms responsible for the glitches. It will help us to understand, like even the crab pulsar, which recently had a large glitch. Previously was only having small glitches. Recently had a large glitch. Does it mean it's now transiting from what is called the usual crab type to the Vela type? These are some of the challenges. These are some of the riddles we are battling to solve. And in one of the, well, this is an X-ray pulsar, possibly a magnetar. I had a pair of glitches that has been described, that has been modeled by either an anti-glitch and glitch pair or two anti-glitches. So which is actually, an anti-glitch is supposed to be opposite the normal glitch, and they are really anti-glitches, because when we look at mechanism, it will need a different physics to explain the existence of such anti-glitches. And so these are some of the riddles. Of course, works are going on in different places by different people, and we are still currently working on some of these interpretations, and we believe that as more observations are available, some of these things could be answered. Thank you very much for your attention.
Thank you, Johnson. Thanks for the nice presentation. I'm just checking if there's anyone with a question. I'm not sure, but I think we're a bit over time. So if you have any questions, just ask on the Slack channel. So we'll move to the next speaker, who is Nikolnya Aima Badalo from the University Joseph Kizerbo, Burkina Faso, and he will be telling us a little bit about imaging of evolved stars. So yeah, up to you, Emma.
Yes, Emma. Hello.
Emma, can you hear me?
Hi.
Hi, Emma.
Okay.
Yeah, you can go ahead.
Okay. Hello.
Yeah.
Do you see my screen?
No, not yet.
Not yet.
Can you just press the green button to share your screen?
Sure. Okay.
Yeah, perfect.
And now?
Yeah, we can see your screen.
Okay. Okay. Hello everybody. Thank you for your interesting in this presentation. I want to for the quality of my English. It is a language that I'm still learning, and before I beg your having said that, I would like to thank everybody. Um, so my name is Badulu. They call me Aymar. I just completed my master degrees um, and I'm currently a doctoral student at the University of Kizego under the supervision of Zakari Kam, Eric Laradec, and Mamadou Ndiaye Nissa. So I offer you here a presentation of what constitute my master degrees with perspective within perspective what will be the subject of our doctoral thesis. So as far as of the master degrees is concerned, focus on the loss of mass the mass loss from algebraic stars, studying the impact of binarity with sure VLT. The mass loss of algebraic stars why? So we recall first we recall that the stars are classified in three categories according to their mass. Thus, we have low mass stars, intermediate mass stars, and massive stars. During the revolutions, the low mass and intermediate mass stars reach a stage called the EGB stage, a asymptotic giant branch stage, where the core is composed of carbon and oxygen. At this stage, the star loses of matter, which will form a shell of dust and gas around the star, and always loss material will contribute to the enrichment of interstellar medium as shown in the figure. We can see also the circumstellar dust path of energy-based stars. We also know that 50% of the dust, interstellar dust, come from energy-based stars, and 90% of the universe stars will one day become energy stars. All this make the phenomenon mass loss of RGB stars very important for understanding the chemistry of our galaxies. So efforts are being made to try to better understand the phenomenon, which is still poorly understood to this day. So Most models suggest that the formation of the dust follows the following steps. First, there is convection and pulsation which produce shocks. Then there is the dust which forms as a result of the shocks. Secondly, we have the radiation pressure that accelerates the dust grain formed. And finally, the dredging of the gas via the collision. In addition, there's a models that consider the star to be alone this stage. However, um, the study of a planetary nebula, a stage following that of AGBs, show that they are rarely spherical. Some of their shapes can only be explained by assuming the presence of a companion, yeah, as in show in the figure. So in addition, more recent study of observation support and confirm the binarity hypothesis. Binarity, in fact, stipulate that the object we see is in fact made up of two stars evolving side by side. We therefore wanted to better understand the mass loss of RGB stars with particular emphasis on the impact of a companion. This guided the formulation of our master objective as follows. We have the search for asymmetry binaries in the core of RGB stars. Secondly, we have the study of a companion effect on the mass loss of low and intermediate mass stars. And for this, we had polarimetric data from three RGB stars, which we reduced for the needs of the study. The method we use is precisely the one of polarimetry that sphere allow us to do. Indeed, as shown in the figure, the light coming from a star is naturally unpolarized, and the figure on the right, which is a polarized flux map of the same star, shows that it emits almost no light. In the part of us, high angular resolution is needed for our goals. We use the instrument providing the best angular resolution actually in polarimetry in the optical sphere. Sphere is the spectropolarimeter, polarimetric for search exoplanets with the high contrast. And we use a simple because it provides the best angular resolution and polarization from that is larger in the optical. A simple is one of sphere 4 tools with ERDIS, EFS, and as an example, it has been used for L2 pupils, the closest AGV star revealing the presence of a companion and is created by the influence of a companion. Alors, so here,
You have 1 minute.
okay,
Yeah.
thank you.
Thanks.
Donc, here we have our master's result with 3 stars, FCPHE, 7 and V1943 SGE, where we can see the asymmetries for the stars. We can see that during our master, we learned to characterize circumstellar envelopes of AGV stars and to model the spectrum of a star. And secondly, we were able to map circumstellar envelopes for 3 stars and to detect asymmetries within 2 stellar radii. And we continue our work with a PhD thesis started in the February 2021 with the goal following first further characterization of the circumstellar envelopes, and secondly study the impact of binarity on mass loss from AGB stars. We have some expectation for this work that are first built to largest catalog of polarization maps of AGV stars at very high angular resolution, and secondly contribution to sphere plus and harmony ALT. Thank you.
Thank you, Emma. That's a nice presentation. I'm just looking if there's anyone with any question from the Slack channel. Not yet. I have a question. So you see some asymmetricities in your data, right? In your sphere images. So could this mean that these are probably binaries? What do you think is the cause of the maybe I might have missed it.
Excuse me, I don't.
I see some asymmetricities in your sphere images.
Okay.
Could this mean that these stars could be binaries? Is there any kind of follow-up on the spectroscopy to check this, or?
Okay. For our stars asymmetries, we use in fact a sphere data. I want to say the data of our sphere stars obtained by sphere. We make some observation with Z-pole. Z-pole is one of 4 tools of a sphere with a resolution of 20 milliards. Okay, donc so with this tool, we make our observation and reduce the data. Simple maker can make the polarization.
Okay.
So
yeah, I have another question from David Buckley. So he says, beautiful sphere images. What is exactly what you're explaining? So what is the level of polarization that you see in these systems? Is it very polarized or not too much?
The level of polarization.
Yep.
Can you repeat? I don't.
So what is so is it very polarized, these systems that you're looking at, or the polarization is very low? What is do you have a number on the polarization? Or if you don't have a number, then we can lead that to the probably the discussion channel on the Slack channel.
I don't have
okay, no worries.
Yeah.
Cool, thanks, Emma. So it was a nice presentation. So we move ahead to the next speaker, who is so this is a recorded one. This is from thank you. This is from Mohammed Darwish. He will be telling us a little bit about masers in massive stars. So, to you, Mohammed.
So hi, assalamu alaikum. Yeah, today, yes, I first of all I would like to thank the AfAS organizer for giving me the opportunity to introduce my talk. Now I would like to share my screen. Okay, can you see it now?
Yes, perfect.
Okay, let me make it full screen. Okay, let's start now. So my name is Muhammad Darwish, and I'm gonna talk about the cosmic maser toward high mass star forming region. I am a PhD, just recently received my PhD, and researcher at the National Research Institute for Astronomy and Geophysics, Egypt. My outlines today are speaking in a short overview about the masers and its history, interstellar maser and maser from massive star forming region in particular, and what we can get from maser observation. And finally, I'll give an example for one of the high mass star forming region. So let's go back to the maser. Maser actually stands for microwave amplification by stimulated emission radiation. Actually, this kind of emission was first described by Einstein in 1950. Here we have a small example. If we have an atom and just we have two levels, this is the ground and the atom here is initially in the excited state. Now we have also another maybe a photon which with energy h nu hit this atom and stimulate it to move to the ground state. And during this process, the atom will give us another photon. So we have which have also h nu energy. So we have now two photons identically have the same energy, and so on for the different process. So the discovery of the maser started from the laboratory by Pasov and Pochov. I think those are Russian people in 1952. Actually, the discovery of the maser was prior than the laser, which was in 1960. And then Towns and Pasov and the other Russian group on the or they received the Nobel Prize in 1964 for their contribution in science. So the interstellar maser, the first interstellar maser was detected by Weaver, and before this in 1965, and before this this detection, there was any idea about the interstellar molecules or the emission coming from the molecules in the space. And once they discovered some things like this emissions, they named it after mystery. Now we have the first interstellar maser. Actually, it's coming from the hydroxyl molecule at the transition 1665 megahertz. So what is the general properties of the maser? The general properties is of the maser can be summarized as it caused by stimulated emission, as we aforementioned. Also, it's extremely small in angular size, highly beam and coherent, actually like maser, and quite bright. Maser also, as we said, required a very specific environment, like the population inversion. So the number of atom in the ground state is less than the number of the atom in the excited state. We can actually find maser from in different phenomena and toward different objects, like in and out galaxies, comets, supernova remnant, and possibly in planetary atmosphere, and usually associated with massive or star forming region. So actually not massive star forming region, but also you can find measure in the low mass star forming region. And if we are going to talk about massive star forming region, I mean by that the stars which is more than 8 in the sun. So in particular, we will talk about those kind of a star and how can the measure trace its formation. Toward this kind of stars, we just have a common measure observations. The first one is the water measure. But let's firstly look at this picture, which indicate that we can find measure from different phenomena in the protostellar objects. You can find measure from the circumstellar disk. You can get also measure from the shocks, or sorry, the outflows. You can also get measure from the shocks between the outflow and the surrounding material. So measure is found in different phenomena in the processor object, which gave it the advantage that you can trace different not only phenomena but also different evolutionary status, and you can also make let's say a sequence or evolutionary sequence based on the measure molecules. The first and the brightest measure is the water molecules. You can receive it at 22 gigahertz, 1.3 millimeter, and also long K band. The brightest, as we said, of all measures. A star forming region, yes, it's detected toward high mass star forming region, both low and high mass, and especially found in the molecular outflow. But in some reference, like our reference in 2020, we can also detect it in some region or some phenomena like the disk, the circumstellar disks around those kind of a star. In addition to the high mass star forming, you can also find it in the galaxies and late type stars. The second molecular or the measure molecule is known as methanol. The methanol measure actually have two classes. The first one is class 1, the second class 2, and those classes are classified based on their pumping mechanism. The first one, class 1, is collisionally pumping, and the second is radiatively pumping. The most famous transitions for the class 1 methanol is 44 and 95 gigahertz, and it's known to be offset from the high mass star forming, the H2 regions. While the class 2 methanol famous transition is 6.7 gigahertz and also 12 gigahertz methanol, class 2 methanol measure. You can detect methanol measure closely associated with the H2 regions and OH and also water measure. But the advantage of this kind of measure or this type of molecules that if you found it in the interstellar matter, you can say that we have a high mass star forming region. So there is no reference mentioned that class 2 methanol measure is detected toward the low massive star forming region. The third one is the hydroxyl methanol measure at 18 centimeter or L band, as we know. Actually, we have different lines, the main lines and the satellite lines. The main lines is basically or mostly detected toward the star forming region at 1665 and 1667 megahertz, while the satellite lines is known to be detected toward the late type stars and supernova remnant at 1612 and 1720 respectively. As we say that it's associated with H2 region, and also some paper related that to earlier stage before appearance of high H2 regions. A more advantage for the hydroxyl measure measure its paramagnetic nature. It's good proper for polarization and magnetic field. So what we can get from maser observation? Actually, we can get too many information from maser observation. As for example, the Heruta and the Vera collaboration in 2020 estimated the distance to the center of the Milky Way from the sun to be 7.92, which is very accurate value. So you can know the distance by using the trigonometric parallax method. You can also know more about the source morphology, like this can outflow, as we say that different kind of maser are tracing different phenomena. Actually, we can also estimate the magnetic field measurements, as we said before. Now, let's take an example for one of the high mass star forming region, which is IRAS 06056 plus 2131, which is very complex high mass star forming region in the outer galaxy. Our observation for the source have been carried out using the Merlin interferometer with angular resolution about 0.2 arc second at the L band wavelengths.
Sorry for interrupting. You have 1 minute.
Oh, yes. So this is an optical view for the center of this at this point, our source. Most of people have seen these things, which is about the channels, and those are the maser spots. So we have here the linear polarization lines. And finally, we can get and using the molecule to the maser molecule or the polarization nature of this molecule to estimate its magnetic field from the polarization from the Zeeman splitting line. So this is the total intensity, and this one is for the polarized light. Our figure is, or this table is actually conclude or summarize our results for estimating the magnetic field, which found to be about 1.5 millijansky. The line of sight magnetic field is 1.5 millijansky using 1665 megahertz. So thank you for your attention.
Thank you, Darwish. Very nice presentation. I'm just checking if there's any questions from the audience. Well, I don't see anyone, but I wanted to know. So in the massive stars, you see these masers. You showed one slide where you had these. You detect masers in these bipolar structures. Is it very related to the maser detection and these bipolar outflows? Because in the low mass stars, we see them very correlated. Do you see them very often in these, bipolar structures?
Okay, so let's go back for the presentation. I think you mean this.
Yeah, it was one of your.
This one. Yes, this one. Okay, sorry. Yes, for this, you can't actually directly relate the maser to be associated with the outflow directly without other observation, but just you have to estimate the absolute position of this maser and compare it with different observation like the CO, which is known to be tracing the outflow. And actually, from the history of the maser, you can test whether this species trace like a Keplerian disk or not. If you have the equation, you can know if it's a Keplerian disk or not. And this is the maybe I'm sorry if I can't answer your question perfectly, but this is from the general shape, you can't judge that from only the measure you can't judge that this is already traced the outflow, but you can collect or make a cumulative work to say that here the measure is actually trace outflow or something like that.
Okay, thank you. Thanks.
Thank you,
Mohammed. So we'll move to the next speaker, which is Oirworth Patrick Abedi.
You're welcome. Thank you.
Kamba. Will be telling us a little bit about ellipsoidal stars from the Kepler data. So, yeah, Patrick. I think it's pre-recorded, so you just wait for it to come live.
The outline of the presentation as follows. I shall give you the introduction, objectives of the work, data and methods, results, and conclusion. Why do we need to study KIC 511-2836? The reason is that there was a previous study in which this particular object, this particular star, was mentioned as being a multiperiodic star of unknown star. The position, the right ascension and declination is given as shown. And again, in the same previous paper, it was reported that this particular star could be a spotted star or perhaps grazing, eclipsing star. However, no conclusion was made for this particular star. On the right is the position or the location of this particular star as indicated, as taken from SIMBAD. And the objectives of this particular work is to be able to analyze the light curve and periodogram by visual inspection, be in position to provide explanations to the different frequencies that will be detected in the periodogram, search for the physical causes of variation in the observed frequencies that will be detected. We want to be in position to explain and suggest possible causes of these variations. Method and data. The data was collected by Kepler satellite. Kepler was launched in March 2009, and it observed over 150,000 stars, and of which KIC 511-2836 was among the stars that were observed. In the figure is the figure is showing Kepler satellite with the field that Kepler observed. How were we able to get this data? The data were downloaded. Take note, the period of observation was for 4 years, and the data is available online. And the link where to download the data is given on this page under data and method. And the data, they were in form of fit file, image file. So one needed to first convert the fit file to readable file. Once you do the conversion, the light curve is given as shown on the top panel in this figure. But take note, this light curve was phased. It was phased with the one of the detectable period of frequency, okay? And if you do light curve beaming with one of the fundamental period of frequency, you get what is on the bottom panel of the figure that is on this particular page. Now, clearly you can see that there are some visible eclipses, visible, visible dips that you see in this particular phased light curve. And these are visible at about 0.2 and 0.7, around there. That's where you see these eclipses. Now, the idea is, the question is, what is causing those dips, those eclipses? And then, as the part of our results from periodogram analysis, I have on the left-hand panel, on the left, what we have is a plot of amplitude as a function of frequency. We see that there are two fundamental frequencies, two main frequencies. The rest of the frequencies that we are able to see are combination of these two. For example, F1, when you look at F1, there is 2F1. 2F1 is exactly twice F1. The same with F2. Twice F2 is what we have here, and so forth and so forth. Now, the summary of the results are shown in the table that is on our right with their corresponding amplitude. Now, the question is, why are we able to see that they are combinational frequencies as a result of F1 and F2? So to be able to interpret this result, what we think, what we suggest is that one, the possible causes of the frequency, the two frequencies that we see, F1 and F2, possibly, they are because we are receiving light from two different stars, and which results into the satellite measuring light from these two particular stars. Or alternatively, we are looking at a binary star with roughly two equal components. That's why we are able to see F1 and F2. That's why we are able to detect F1 and F2. Another possible explanation is that the light variation that we see in the light curve and periodogram, the dips that we see, the eclipses that we see, are due to spots, with the first frequency being from one star and the other one coming from the other star. The fourth possible explanation is that two different stars are being measured by the satellite. Conclusion. What can we conclude from this study? The conclusion is that we have found that KIC 5112836, which is a star located in the field of an open cluster NGC 6819, is possibly a binary, as supplemented with the results of frequency F1 and F2, and the most logical deduction is that possibly these are due to binary motion. It is also suggested that to be able to do any confirmation to the result that is obtained in this work, more radio velocity measurements should be carried out so that one is able to make a convincing conclusion, a conclusion about the nature of this particular star, KIC 5112836. Thank you. Any question?
Thank you, Patrick. In our talk, I'm just checking on the Slack channel if there's any question so far. Just wait a little bit. No, I don't see any questions coming. No. So I have a question. So you mentioned that are you monitoring this star with radial velocity, or you're looking for archival data to look for spectroscopic measurements? How are you planning? Is there anything done in that area?
Yes, thank you for the question. We plan to monitor the radio velocity measurement of this particular star in the next campaign. At the moment, in the archival data, we only have one measurement of radio velocity.
Yeah. Cool. Thank you. So yeah, we move to the last speaker of this session, who is Ambeleleni Davids from University of Namibia, and he will be telling us a little bit about globular clusters in the Cherenkov telescope array. So, Davids.
Hello, everyone. So my name is Ambeleleni Davids, and I would like to talk to you about estimating uncertainties in the predicted gamma ray flux of globular clusters in the Cherenkov telescope array era. And in this work, I collaborated with Prof. Christoph Fender and Dr. Andreas Kopp and Dr. Michael Backes. Globular clusters, or in short, what we call them GCs, are actually gravitational bound old stellar systems, and they consist of about 10,000 up to millions of stars. And of course, they have ages ranging between 11 and 13 billion years. And as such, they are the oldest surviving stellar subsystems in galaxies. So most galaxies, including the Milky Way, are actually surrounded and penetrated by a system of these GCs. And of course, our galaxy has about 160 globular clusters. And of course, this is an image of a galactic globular cluster, TESN5, which is the only galactic globular cluster that has been plausibly detected at very high energy. So globular clusters are spherically distributed about the galactic center at an average distance of about 12 kiloparsec. And this figure basically just shows how GCs are actually distributed around the galaxy. So the black cycles that we see here, or the black dots, actually just indicate the positions of GCs according to Harris Catalog 1996. Of course, there exists a large variety of exotic objects that populate the dense environment of these systems. And of course, these objects include things like black holes, millisecond pulsars, white dwarfs, and so on. And of course, these systems are actually visible from radio to gamma rays, and as such, they are referred to as multi-wavelength objects. So in our work, we basically focused, we want to assess the uncertainties in the predicted VHE gamma ray flux of GCs for a given electronic model, and also to give theoretical guidance to CTS observational strategy. So what we did is that we modeled the IC gamma ray flux expected from several GCs so that we can see whether the predicted flux can exceed the CTA sensitivity, and also to see if we can actually satisfy the Hess upper limit, of course, with a range of predicted fluxes due to parameter uncertainties. So we will in this work, we modeled a population of GCs and actually compared the predicted integral fluxes with Hess upper limits. So we also modeled two sources, that's basically the northern hemisphere source, which is M15, and also omega sen, and then compared our result with differential flux upper limit. So in our work, we basically focused on the VHE components. So the model of COP that we basically used calculates the particle transport, and it includes diffusion and radiation losses. And of course, in a spherically symmetric stationary approach, it also predicts the spectral energy distribution from GCs for a very broad energy range by considering unpulsed SR and IC. And the model also assumes pulsars to be the sources of relativistic leptons in the GC, and that pulsars are actually located at the center of the cluster. So the main three parameters of the models are basically the cluster magnetic field, that's B, and then we had the parallel index of the injected particle spectrum gamma, the number of stars in the cluster, the distance to the cluster, and we have the average spin down luminosity per pulsar. Then we have also conversion efficiency of spin down luminosity into particle acceleration eta, and the number of millisecond pulsars in the cluster. So actually in 2015, Fender and COP applied electronic GC model to a population of clusters that were measured in Abramowski 2013. So whereby they actually predicted the lifetime averaged flux and compared it to Hess taking upper limits. So they actually found that none of the predicted single cluster spectra violated the Hess TV upper limits for individual sources. So, however, they actually noted that different choices of parameters will actually lead to average fluxes that in some cases might actually end up exceeding those limits. And that's why we are actually refining their calculations. Of course, we are including an estimation of uncertainties on the predicted VHE fluxes. So we basically used a Monte Carlo technique so that we can calculate the single GC and also the stacked integral VHE flux of 15 GCs, of course, with uncertainties due to the uncertainty in model parameter. And of course, we did this by randomizing over 7 free parameters, which are here. And we actually note that, of course, for a finer grid, this basically leads to a smoother distribution of fluxes. And so we calculated the integral flux for a number of trials so that we can obtain the convergence of number of this. Your number of trials basically exceeds the number of combinations, or when it approaches the number of combinations. We also know that actually undersampling will not give a smooth distribution, but if you oversample, then you get a convergence. So we also checked for the convergence of the source strength parameter using two methods, of course, using 47 tag as an example. And as for the first method, we actually picked values of 4 relevant different parameters on a specified grid, while as for the second method, we actually randomized over the same 4 parameter, and we conducted 1 million trials for both, in both methods. And of course, the 2 different methods gave very similar results. And of course, with the 2 peaks in the histogram, which are just only slightly shifted with respect to each other. So one can basically say that assembling on a grid versus when you randomly pick parameter values does not actually make too much of a difference in terms of the distribution of Q naught. So as for the differential flux predictions, so MAGIC has recently published differential flux upper limits for M15. And of course, we applied again the model of COP to this source so that we can obtain the differential fluxes for each combination of 7 free model, for several combinations of 7 free model parameters, and also calculated the final differential flux. So we estimated the uncertainties and the differential flux of M15 at 13 different observer-defined energy bins, and we logarithmically interpolated model fluxes so that we can basically obtain predictions at the specified observational energies, which is basically associated with the upper limits. So we also use the same method for this source, omega sen, and so that we can calculate the differential flux. And for both sources, we basically used about 10 million trials. So we then plotted the weighted flux as a function of number of trials, whereby we did this for about 100 million trials for all the 15 GCs at a threshold energy of about 0.23 TeV. And then we calculated the weighted flux for each of the globular cluster. Of course, we chose 2 sets of parameter combinations. For the first parameter combinations that we chose, we know that the medium stacked flux actually exceeds the upper limit, of course, by a factor of about 8. And we therefore had to consider a second parameter set where we had to reduce the main free parameters that basically that are used basically to determine the source strength Q naught. That's basically your eta, E dot, and number of millisecond pulsar. And we reduce those 3 by a factor of 3, just to show that if you lower your Q naught, then of course the flux limit might be satisfied. So here we are not re-saying that the second choice of parameter is the final answer, but we are just considering this range to be still realistic, of course, given that the uncertainty which is in their intrinsic values. So in the second case, of course, the predicted median flux was a factor of 4 below the Hess upper limits. So we then summarized the fluxes that we obtained for both the stacked as well as the single GC cases. And of course, the black diamond and the squares and the arrows basically correspond to the observational upper limits, while the green and the blue error bands are for the median fluxes, and of course, 1 sigma uncertainty interval for the 2 different parameter combinations that we chose. So we know that there are, of course, indeed parameter combination that will give you fluxes which will be below all these observational upper limits. And then as for the M15, so we actually, this is one of the densest GC that ever discovered in the Milky Way galaxy. And it has about 8 millisecond pulsar. And of course, no detection has been net detection from the direction of this source has been actually made in the TeV. And Asiari found an upper limit, which is basically a bit more stringent than the one that has been published earlier by Abramowski 2013. So we then created a distribution of the differential fluxes and also calculated the medium and also 1 sigma uncertainties of the log of those fluxes. Of course, by finding the 16th, the 50th, and the 84th percentiles. And of course, as before, we again did this by randomizing over the 7 free parameters. And we did this many times so that we can study the convergence. And this figure basically just show the upper limits from the 165 hour of MAGIC observations on the differential flux, and also the predicted spectrum for a different combination of model, and of course the medium and with the median point with 1 sigma error. So in here, we just know that the differential data are much more constraining than the integral data, because here we have 13 points of comparison instead of 1. And of course, here we can see that for each bin, one can actually tell whether the model exceeds the flux at that energy bin or maybe not. And of course, constraining this spectral shape. So for our choice of parameter, we actually satisfy the MAGIC flux upper limits. And of course, we applied the same method to omega sen again. And of course, in this figure, we just compared the predicted differential fluxes with the Hess and the CTA sensitivity curves for about 400 hours of observations. And we also indicate typical predicted gamma ray spectra for a few choices, of course, few choices of parameter combinations. So we basically know that our current IC predictions are actually higher than the one that has been predicted in Javala 2018. So in conclusion, so we focused on assessing uncertainties in the predicted VHG gamma ray flux of GCs, of course, to give theoretical guidance to CTA's observation strategy. And we basically confirmed that a finer grid in parameter space basically leads to a smoother distribution. And also a larger number of trials will lead to convergence as your number of trials approaches or basically exceeds the number of combinations. And we found that even though none of our predicted individual cluster median fluxes plus uncertainties were violating the upper limits, actually our total integral weighted flux violated the Hess upper limits for our first set of parameter combinations. However, one has to be careful to just get rid of the model or to just discuss the model just because your calculations for the best guess parameters exceed the observational limits. Of course, keeping in mind that the uncertainties in prediction that might come from the uncertain parameter values. And as for M15, we actually found that the differential flux upper limits were more constraining than the Hess integral flux upper limits. Yet we could still satisfy those upper limits for typical parameters. And we also calculated the TeV flux for omega sen, and of course indicating that this source omega sen might be actually a possible candidate to be observed by CTA or Hess. So we therefore know that if increasing measurement accuracy on model parameters will actually improve prediction of GC fluxes, and this will provide, I think, a better guidance to CTA observations. And of course, I put a link here for our paper, and I think that is basically it that I have, and I thank you.
Thank you, Ambeleleni. We'll just check the Slack channel if there's any questions for you. I don't see any yet. So I think that will be it for this session. So I would like to thank you and all the speakers from this session. We will now have a short break of around 10 to, I think, 12 minutes before the last session of today, which will focus on the IEV General Assembly that is planned to be held in South Africa in 2024. So please note that this session will not take place on the Event Air platform, but on the Zoom a link has been sent to your email by Charles. So yeah, keep that, note that. Thank you. Bye. See you later.